Thanks, I'm Jean Rollenas. My background is in communications, and I moved into the lighting field not so long ago. But then suddenly we had this challenge and this opportunity to communicate via light, to use the LEDs here in the ceiling for communication. And I'm seeing all my colleagues jumping on this, but the models and the ideas coming from radio communications, they apply very well to what we do here with LEDs, but there are some subtleties where it completely goes wrong. And I intentionally use the word goes wrong. And that's a debate that I'm also having with my PhD candidates here, like Thiago in this room, Chao Chen, the co-authors, and I'm constantly debating what is a good model for the LED. Now, being here at this conference, which is now called Sustainable Smart Lighting, but used to be called Light Sources, that is the place where I like to have your input and feedback on how we should model the LED for optical wireless communication. So the power consumption of the LED and communication of light, why are we doing that? If we use the light here to communicate, we are not interfering with the people next door. So different from radio, we can really reuse the spectrum much more efficiently, and we have huge amounts of spectrum available to do our communication. Then the question is, how green is it? How energy efficient are we? And I think Professor Harold Haas really pitched this topic of doing wireless communication via LEDs. We have 2,600 times the spectrum, the entire spectrum of radio, multiplied by 2,600. That is what we have available. We modulate white light, and then we use 1,000 times the entire radio spectrum just for one stream of about 30 or 300 megabits per second. So where is really the problem? And that has a lot to do with the energy per bit that I'm capable of using. And when we talk about energy per bit, the fiber guys are thinking in terms of photons per bit. Radio people usually think of energy per bit. And if I may summarize decades of research in radio communication, it's all about what the mathematicians call the L2 norm. The integral over the signal squared, and the integrate over time. That's the energy that we can get together to emit a bit. And the bit error rate is also dependent on the distance between two signals squared over time. And in radio communication also, these norms determine how much power we need to feed into the antenna. And then people apply that in scientific paper to optical wireless communication. And then they say the energy of the signal is, the variance is the expectation of x squared. Thinking of an antenna that acts as a 50 ohm resistance, but they use an LED or a laser. But in order to create a photon, I have a fixed voltage, more or less fixed voltage. And the power that I emit is that voltage multiplied by the expectation of the current, and not the expectation of the current squared. So what I'm saying is that whole theory of radio communication collapses. And still we see hundreds and thousands of papers doing this. And that's why my PhD candidate volunteered me to take the heat of that discussion and see how we can improve the modeling of that. So what we try to do, and I invite you to read the full paper of how we are modeling the LED, we of course use the Shockley equation stating that the voltage and the current have a very nonlinear behavior. You need a certain junction voltage, and from there on you see a bit of a differential resistance. You see something that acts as a resistance for a small signal. But first you have to come across that voltage of approximately 2-3 volts. Now if we describe the power consumption, we see that the power lost in the DC bias, after doing some math, including the Shockley equation, more or less is like this voltage multiplied by the variance of the signal, where we have this parameter Z of how much margin we have to extend. Similarly, and that's an interesting result, for the modulation, we also see something that is proportional to sigma, the standard deviation of the modulation of the signal. Not the variance, the standard deviation. It's not sigma squared. Whereas in this final term, where we basically say that in addition to the photonic effects of the LED happening somewhere in the junction, we also have a parasitic resistance. And if you just apply the parasitic resistance, we all get back the things that we would expect. So the parasitic losses indeed are the variance. The variance is then if you square multiplied by what I lose in the resistor, and I also lose something on the DC bias. So there the squares come back. But if you make better and better LEDs, and your community here may know how to make these LEDs better, this term is going away, and we basically have this constant voltage multiplied by the average current and variations. There are a bit of interesting details about what is happening to the modulation, where we see that dynamic resistance. But still, if we apply the effect that the DC bias is also a function of how far I modulate the signal, then again, we see that the dynamic resistance also depends on how much I need to swipe with the modulation. So putting that in a couple of curves, we see a very similar result here. We see that power consumption is linear with the current. We see straight lines. And only if you add something that we do not want and that our engineers are taking away, we see that squaring. Whereas people who are just borrowing for radio engineers forget about this part and say everything is quadratic. And in my opinion, it's not. So this is also an interesting experiment that radio engineers see very different behavior. If I take a single LED, I have a pulse of amplitude A for a certain duration TB, my bit time. I could use two LEDs, reduce the time, but I split my energy. So playing the game fair, and then suddenly at the again playing the game. Maybe for so we see a different role. What does that mean? What is the performance but before I do that, what I see, why? Huge current the efficiency. And in order to be able to see full derivation, we see something. Well, going to micro-LEDs is good, but communication over is very hard. What is happening if you go to micro-LED, basically we shrink current density. Amperes going up. One of the factors in electrical volt efficiency. There is a larger the quantum efficiency do nothing, but it's something that I will not go into too much into detail. But you gain bandwidth. So, to look more into details of these curves, if we take micro LEDs, basically what we're doing, we are increasing the current, or at least the current per square millimeter. And the LED becomes faster, but it's mainly because of recombinations of holes and electrons that are lossy, that are non-radiative. So you make the LED faster, but the only thing why it gets faster is because holes and electrons find each other without emitting a photon. And the radiative part also goes a bit faster, but not to the extent as you see the LED becoming faster. So on that aspect, we would say, be careful with relying too much on that effect because you lose a lot on signal energy. You count photons per bit or energy per bit. It may not be a good idea. The quantum efficiency is also something that is less efficient. People know that if you go further into the droop, if you push the LEDs more to the limit, the efficiency will go down. So that's not really the effect that you want if you want to cover a full room. And then that's combining all these ideas together. If I'm taking into account that if I'm increasing the current density, go to micro LEDs, I gain in bandwidth. So basically this parameter zeta that plays a large role in the papers. How many of these LEDs am I putting in parallel? My reference is zeta is 1, I'm taking 1 LED. If I make zeta is 20, that is the black curve here, that is basically having 20 LEDs in parallel. And what does that? Well, it reduces the current density in each and every LED. In the end, I get the same power out of it, but I load each of the LEDs lower. That's bad for the bandwidth. For the bandwidth, I should make the zeta less than 1. That's basically cutting into the die and doing as if I have half an LED. So the same power with a higher current density. I gain in bandwidth. But the throughput that I get, the number of bits per second that I can feed through, is of course dependent on the bandwidth. But it's also dependent on the signal to noise ratio, or the strength of the signal. So if I'm increasing current density, the quantum efficiency goes down, the wall plug efficiency goes down, and in the end, the interesting curve here is this one. What is happening to the throughput that I get if I really normalize the result? So I'm trying to play a fair game, and I say, how much power would I need to cover this room to make sure that we have a signal everywhere? So then, basically, I'm calculating back how much power I need in every LED, and how I spread that over the entire area. And then I can calculate the path loss. The simple model there is, we throw photons into this room everywhere, and we just have 1 square centimeter where I capture the photons, and that is the signal that I'm trying to detect. So green is our reference, and what we would see is that basically if we take many LEDs in parallel, that would help. So going down in current density, being very relaxed and not using the LED where it is the fastest, but going for efficiency. If I'm going to micro LEDs, I'm not gaining. I'm gaining in bandwidth, and if I have more power, I would think, well, I have more bandwidth, more power, so that would help me to get more bits per second. But then still I have to cover the entire room. So if I then also start to calculate how much micro LEDs I would really need to cover the room, it tells me that I need quite a bit of power there. That is how far as we go into the analysis. I also hope that I've shown to you that having the proper models for the LED are really very useful to evaluate these kind of LiFi communication systems, to determine whether these kind of communication systems are really green, whether they are power efficient, rather than, and that is honestly what I see in a lot of scientific papers, I got a world record on having so many gigabits per second. And then you really need to see the fine print and say that the distance over which they communicate is not too far off from creating an optical probe. All right, so yeah, and I think that those are the kind of takeaways. I think it is a very interesting field also to think in terms of what are the LEDs that we need, how to design these systems, how can we combine a lighting system with a communication system. And there's still many things to be done. And sometimes I feel that the community presenting papers there is a little bit single-minded on one parameter, more or less. They build a Formula One racing car, but not the one that is the agile car that goes through the city streets that are very congested and where we want to have large coverage of the system. So I also like to end with a kind of call for help. I would like to see whether we can have the right context to improve the models of the LED. There are possibly more losses. There are also the effects that there are, you charge up the LED, and so it's a kind of capacitor, there's a parasitic inductance, and all these things determine the power consumption of a LiFi transmitter.